Hi, this is Dr. Staley, and today we are going to be doing the spectroscopy experiment. Specifically, we're going to look at the absorbance of red 40, which is a proprietary name for the dye used in Kool-Aid. Now what we're going to be doing is we're going to be measuring the concentration of this dye in a sample of Kool-Aid that is made to standard strength. But in order to figure out the concentration, we first have to figure out how much it absorbs in the first place. And that means we need to make a calibration curve. So here we have Allura Red, aka Red 40, at a very specific concentration. This is a standard. This is a stock solution that is much more concentrated than what we're going to be using today. And here we have a set of volumetric flasks that we're going to be using in order to make the dilutions, along with volumetric pipettes, so that we know how much of the stock solution that we are delivering, and we know how much we are diluting them by. Now, volumetric pipettes are glassware that is designed to, and normally they're calibrated with water. They're designed to deliver a very specific amount of volume, and no more and no less. You fill them up to this line right here, and then they hold a certain volume. In this case, this one holds 5 milliliters. But it actually holds slightly more, because what happens is, on the end there, when the solution has run out, a little tiny droplet is going to be left. This is calibrated with that droplet in mind, so we are going to be using this to deliver exactly 5 milliliters. Just like this one, we're going to be using to deliver exactly 10 milliliters. Just like this one, we're going to be using to deliver exactly 20 milliliters. And likewise, we have volumetric flasks. Unlike the volumetric pipettes, volumetric flasks are designed to hold a very specific amount of solution. Not to deliver, but to hold that amount, so that the solution that you make in the flask has a volume that is accurate to a very high degree. Likewise, they are labeled. This one holds 100 milliliters. This one holds 25 milliliters. Now, in order to make our standards, we are going to have, so this thing right here is the spectrophotometer that we're going to be using. We're going to make 5 standards. 1, 2, 3, 4, 5. The idea is that we're going to dilute this by a 10-to-1 ratio by putting 10 milliliters of this in here, and then filling the rest of the way to the top by with DI water. Then we're going to transfer different amounts of solution out of here into each of the others, so that, and we're going to dilute each of these by a certain amount also. Sorry, we're going to dilute each of these by filling up to the line also. Now, the reason that we do this, so the idea is that the most concentrated solution and the least concentrated solution are two extremes. And the concentration of the dye itself in the Kool-Aid that's made to regular drinking strength should be somewhere in between those two extremes. So that when we plot this on a graph, we should ideally get a line, and then because the line is the result of the concentration and absorbance of the dye in each of our standards, when we run the drinking strength Kool-Aid, the absorbance will be somewhere in between the two extremes because the concentration is somewhere in between the two extremes. So when we plot where the absorbance is on that line, that will tell us what the concentration is. Okay, so here we go. Oh, and lastly, there's the pipette bulb. So this is designed so that the ends of the pipettes go in here, and then you can squeeze this. It holds its shape. Then using this lever right here, you can suck air into it through the bottom, which also sucks solution up through the pipette. Then when you want to deliver some, you take this and you press it down, and that opens the top of the pipette to the outside air. Now, when we reach the end, if we want to blow at the end, we don't have to, but if we want to, we use this right here. This compresses a little balloon, and that will push just a little tiny bit of air through the pipette. So, let's start at the beginning. And here I'm actually going to move these out of the way so that I don't end up dropping them like that, and so that I don't end up moving them, knocking them over by mistake. There we go. So we want a 10-to-1 dilution here. So I'm going to squeeze the end of the bulb. Put this down to, oh, I almost made a huge mistake. That huge mistake is really quite simple, and that is we don't want to put glassware directly into the stock bottle if we can avoid it. So what we do instead is we pour a little bit of the stock solution out. And that way we do not risk contaminating the stock bottle. Put that out there too. Oops. Yep, that is not 10 milliliters. And this, ladies and gentlemen, is exactly why it is good to trust the markings on the beaker as little as possible. Because I filled it up almost to the 20 milliliter mark, and yet the amount that's actually in there is only about 8 or 9 mils. There we are. Okay. Now there's a little bit left inside the tip, but there's also a drop hanging off. And we want the drop to go down also. So we touch that against the side. And we let it go down. And then we're going to use this later, so we want as little of the drop inside there as possible. Now what we do is we fill this up with DI water. Okay, so now that we've got standard 1 made, we're going to make all the other 4 standards. So that's standard 2, and I will add DI water to that in just a moment. First though, 3. Now standard 3 is going to be slightly more complicated than standard 2 because I have to use the same pipette that I used before. And I have not gone and given it a really thorough cleaning in the meantime. So that means it still has little droplets of the original stock solution in there. So what I want to do, so I put that in standard 1, and I want to just rinse the whole thing with the standard 1 solution. So since this solution is what is going to be delivered, I want to make sure that all of the droplets on the inside of the pipette are from this solution. And the change in concentration that's in the volumetric flask here is small enough, is going to be significantly smaller than the change in concentration would be inside the volume of everything inside the pipette. Okay. So now let's put you off to the side and add the DI water to you. Okay, now standard 4 is going to be a lot like standard 3. Here I need to add 15 milliliters. And so same solution in the 10 ml pipette that was in there before, so I don't need a separate rinsing step. And make sure to touch the tip to the glassware to get that last little droplet up. However, there is also the interesting solution of number 5. So in order to get 15 milliliters, I'm using both the 10 and the 5 milliliter volumetric pipettes. But in the case of the 5 milliliter volumetric pipettes, it's been sitting around for a minute or so. And in that time, some of the water in the droplets that were inside it could have evaporated. So just to be on the safe side, I'm rinsing it with the solution to be delivered first. And then I'm taking the solution to be delivered to make sure that the concentration is really, really well known. Okay. And then for standard number 5, I can just, this one is supposed to have 20 milliliters of standard 1. So that means I can just use a 20 milliliter volumetric pipette that is already nice and clean. Just drop to the side right there. At the end. Okay. There. So now I'm not going to put more DI water in standard 1 because I want standard 1 to have the same concentration it currently has. But I do need to fill up the rest with DI water, so that's what I'm going to do now. Okay, and we're back. So, got everything nice and set up. 5 standards here. The solution that I used from the density experiment, because I actually did that earlier today. And we are good to go. Now, for this experiment, we are going to be using the Spectronic 200 spectrophotometer. We have it set to 501 nanometers, which is the highest part of the absorbance spectrum for the dye that we are looking for. And in the side here, we have cuvettes. So cuvettes are what we're going to put first our standards, and well, first our background, then our standards, then our actual experimental solution in. They are going to go in here. So the cuvette goes here. The light source is over here. Actually, the light source is over here, but it has mirrors inside that bounced around. So the light's going to come through here. Some of the light will be absorbed, some will not. The light that does not get absorbed will go out here and will go into the detector over there. The way that let me put this down first. Now, the way that the spectrometer works is that it knows is that first it measures the intensity of the light that's going through when there's no sample, and then it compares that to the intensity of the light that's going through when there is a sample. However, we don't want just that, because there's more than just the dye in our sample. There's also sugars, there are salts, and there's water. Now the important thing here is the water, because the rest of it doesn't absorb very much at all. And the water also doesn't, but the water can refract some of the light. So that will cause the measured absorbance to be lower than it would otherwise. And as a result, what we need to do is we need to take a background. So the background in spectroscopy, the background is everything except the thing that you're looking for. So hypothetically, to get a good background, what we would want is absolutely everything in the solution except for the dye. But we can't really do that. Well, we could, but it's a pain. So for this experiment, we're just going to put DI water in as a background, and we're going to call it good. Now, we're going to be putting it in one of these cuvettes. One of the important things to note about these cuvettes is that not all of them have sides that are completely equal. So this one does. Actually, it looks like there's a tiny scratch on the bottom here, but the bottom part here is not where the light goes through, so that scratch does not matter. So this one has all sides being very clear. Some cuvettes have two sides that are made extremely clear and two sides that are made extremely foggy on purpose. The reason they do that is so that you have two sides that you can always grab and not have to worry about putting fingerprints on, because they're already foggy, so you're already not going to use them. For those cuvettes, it's important to look at the top right here, because there will be an arrow on the two sides that the light is supposed to go through. But like I said, the cuvettes that we have at Southwestern, they don't have that arrow. Also, try and make sure that you hold it by the frosted piece up here. So, first things first, we are going to take our background scan. Get in there, nice and good. Now, before I put this in there, I'm going to wipe it off with a lintless wipe. So these are Chem wipes from Chemtech. They are basically really soft tissue papers where, for all intents and purposes, all of the lint has been removed. So you don't have to worry about stray fibers getting onto your glassware, wiping your glassware down with Chemtech. So I'm putting the cuvette in the holder. I'm going to take a background, which in this case is the button that has a bunch of zeros on it. And it says performing, performing, performing. Alright, so it has its 0. Now I can take this out and I can dump out this water. I'm just going to be using this as a waste container for the time being. So, now I want to put my first standard solution in here, but I've got a problem. There are little droplets of water on the inside of the cuvette. So if I put my standard solution, well, any of my standards really, or even the experimental mixture in there, the concentration of the dye is going to be slightly lower in here than it is in there. The way that we solve that is we start off rinsing the cuvette with whatever solution we are going to put in it. Oh, I need to clear something up. So we're only going to put about 2 or 3 milliliters in each of these cuvettes. We don't need the full 10 mils. So normally what I would want to do is I would want to use a small disposable pipette. However, because this volumetric flask is so big, a small disposable pipette won't actually reach all the way to the bottom, which means that I won't be able to get which means that I'm probably not going to be able to get enough standard out in order to fill up the pipette. So I'm using the longer volumetric pipettes. I'm using the longer volumetric pipettes because they have a longer neck and can actually reach to the bottom. In this case, I'm not actually filling it all the way full. I just want enough so that I can first rinse and then fill. Rinse that side. Oops. Once again, this is a good use of a Chem wipe. Okay, so now we've still got some droplets in there, but the droplets already have a concentration of dye that is really close to the concentration in the standard. So what that means is that I can go ahead and get some more standard. I can put it into the cuvette without worrying that I will have a concentration that is measurably far off. And once again, we want to wipe the sides down here. Alright, so absorbance for 1. 0.94. Okay. So we're good, and now we just do the other 4 standards. Okay, I'm now done with all 5 of the standards, and it is time to do the actual experimental solution. So here what I'm going to do is the same thing that I did with the standards. I'm going to rinse this out with some of the experimental solution, and then rinse the cuvette out. Here we are. Now the moment of truth. So the most concentrated standard that I scanned had an absorbance of 0.94, and the least concentrated standard had an absorbance of 0.15. So this one, the experimental sample, has an absorbance of 0.33. So its concentration is really close to standard number 3, which had an absorbance of 0.37. Now, I'm not going to do the analysis. That is for you to do. I will provide this data in a PDF that you can download, and you can do the analysis on your own. Thank you very much. Have a nice day.